Hello, I'm back again, and I am going to do some experiments with a thermopile. A couple of weeks ago, I had an outdoor fireplace that stopped working, or I could not light it. The pilot light would light and stay lit, but the main gas valve would not turn on. I did some troubleshooting and determined that it was the thermopile. The thermopile is what provides the electricity for the control valve to work. And it was a little tricky to find out what the problem was, because this thermopile looked like it was working. So what I've got going on here is I have a small just propane torch, and I have it turned down to a very small flame to kind of simulate what a pilot light might look like. And I have the output of the thermopile connected to my Regal DL3021, and we can measure the voltage and current. So when I was working on fixing this fireplace, it kind of got me thinking about energy harvesting and how much power can we generate with one of these thermopiles. I looked at quite a few videos, and most of these videos just had discussions about voltage. I couldn't find anything that discussed current. Well, that's what I'm going to do. We're going to look at current and power that you can generate from a thermocouple, or I'm sorry, a thermopile. So this is the thermopile that I pulled out of the fireplace that is not working, and was measuring about 0.7 volts. And so I was looking at it in an open circuit mode, and it looked like it was good. I pulled out the device and started putting the load on the thermopile, and saw that it couldn't supply much current, but I had no idea about what a thermopile should be able to supply. This is the bad thermopile. I am going to start with 10 milliamps. And at 10 milliamps, our voltage is dropped to 0.45 volts, and this is simulating a 47 ohm resistor. 20 milliamps, and we can see that it is basically turned off. 10 milliamps is kind of the maximum current that we can pull from this thermopile. I now have the new thermopile attached, and we have about the same distance and the same amount of flame, and our open circuit is approximately 0.6 volts, so fairly similar to the Feld thermopile. And let's start adding some current and see what it does. Ten milliamps, 20, 30, 40, 50, 60, 70, 80, 90, 100. So let's go to maybe a half voltage setting. A load of 60 milliamps. Our voltage is dropped in half, and that is simulating basically a 5 ohm resistor. So this is interesting. So you basically can get 20 milliwatts out of a good thermopile. So that's what made fixing that fireplace a little tricky, was that the open circuit of the good and the bad thermopile, the voltage rating was about the same. The thermopiles have cooled down. I've waited about a half hour. This is the bad thermopile, and we can see that we're measuring about 26 ohms. Here's the good thermopile, and we are measuring about 4 ohms. So not powered up, you can clearly see that there is a difference. I guess they powered up, not heated, I guess is what I should say, that you can see a difference. So I took apart the Feld thermopile, and this is what it looks like in the inside. I had no idea how they were built. I've put up a little piece of cardboard, white cardboard here, so hopefully you can see this better. And this is pretty crazy. So there are approximately 30 connections on the top, 30 connections on the bottom. This is all just coiled up, compressed, and put inside the jacket here. But what is interesting to me is, so every other wire here is going to be a dissimilar metal. But since they've done this, you're going to have all the positive voltage generation on this side and negative generation on this side, or vice versa. So if you had this little bundle here and the heat on the top and the bottom was the same, you would get 0 volts out of this bundle. You need to have one end hotter than the other end to maximize the efficiency of this bundle. So that's really interesting. So we are going to do some experiments with heat at the top or the bottom, or flip it sideways to see if we can get an even heat and see what type of power we get out of this thing. This is interesting. I have the flame pointed about halfway on the length of this thermopile, and I have a 50 milliamp load programmed here, and we're getting about 17 milliwatts of power. This is simulated about 6.7 ohms. I can turn this load off, and we get up close to this to the 0.6 volts that we've typically been seeing. I'm going to turn the load back on. It's alternating plus minus, plus minus, plus minus. And so if the heat was the same on both of these ends, you, I think, theoretically would get 0 volts or 0 power. So what I'm going to do is I'm going to turn this thermocouple horizontal so that both ends get the same amount of heat, and we will see what our power drops to. So we can do this without getting burned. So I'm trying to hold this approximately in the middle, same distance from the flame. And our power is rapidly dropping. We're down to 5 milliwatts. Now I'm going to move it towards the end a little bit. and we can see that our power is now increasing. So that really does show that the dissimilar metal connections in the thermopile are alternating between plus and minus voltage. Let's wrap this video up. I have a single element here of the thermopile. We're measuring about 0.16 ohms, and we will put this in the flame and see what type of voltage we get. DC volts. So this is going to be a lot hotter than it is inside that case, I think. So roughly 60 millivolts. Interesting. And there are 30 connections inside of this piece on one side. So 30 times 50 would be 1.5 volts, I believe. And that would be the theoretical max. So maybe 1.8 volts if we took that 60 millivolt number. Anyways, pretty interesting. So hope this was interesting for you. It was for me. I did not know how these things were made. So if you have any questions, let me know. Thanks.